Good afternoon, everyone. Mr. Armkey back with you for CTI 120, and today we're going to talk about Chapter 6, Wireless Networking. Our objectives for Chapter 6 are to identify and describe some different types of wireless networking characteristics, some of the various wireless standards that support the IoT, or Internet of Things. We're going to look at some 802.11 standards and innovations, and we're going to look at how to implement, secure, and troubleshoot a wireless network. Wireless networks, also called WLANs, wireless local area networks, are networks that transmit signals through the air via radio frequency instead of using a backboned cable network, though those will be involved. Now, wired and wireless signals will share many similarities. They use a lot of the same upper protocols. The only differentiation seems to occur at layers 1 and 2. The nature of the atmosphere also makes wireless transmission different from wired transmission. The temperature of the air, the elevation at which we are transmitting, and then potential interferences such as heavy congestions of dust or things like that, trees. The wireless spectrum is the frequency range of electromagnetic waves used for data and voice communication. This is going to span frequency ranges, or what we call bands, between 9 kilohertz and 300 gigahertz. Now, some bands only have a single frequency, which is called a fixed frequency for that band. Some will have multiple frequencies. So if we look at cellular, for instance, we can see that there is one that is around 800 megahertz, and then there's one that's at about 1.8 gigahertz. So we see that there's some separation there. We see that Wi-Fi exists at around the 2.4 gigahertz mark, and then just at 5. So we see that there are some overlaps with different types of signal bands for each type of communication. Now, most wireless devices will implement one of two technologies, what's called frequency hopping or direct sequence spread spectrum transmission. Now, each wireless standard in the 2.4 gigahertz range, the most common, uses its allotted band as follows. Wi-Fi uses direct sequence, as does Zigbee. Bluetooth uses frequency hopping, and ANT Plus uses a fixed frequency, which does not use direct sequence or frequency hopping. Now, the purpose of the antenna is to be able to emit and receive electromagnetic signals. So wireless signals are going to originate from a current traveling along a conductor. That's going to be a wired network that connects to the back end of the wireless perimeter. So the transmitter passes the signal to the antenna emits the signal, transmits to the other receiver, which converts it back into wired current. Now, both antennas have to be tuned to the same frequency in order to use the same channel. That's why knowing what band a particular device operates in is so important. Now, antennas do have a radiation pattern, the relative strength over a three-dimensional area of all electromagnetic energy that an antenna sends and receives. If it's a unidirectional antenna, the signal will be issued along a single direction. An omnidirectional antenna, on the other hand, will issue and receive wireless signals with equal strength and clarity in all directions. So unidirectional is focused, omnidirectional is what we call a radial antenna. The range of an antenna is its reachable geographical area and will change based on the amount of power put into the transceiver connected to that antenna. Signal propagation is the way in which a wave travels from one point to another. The analogy I often use is if you drop a stone into a pond, you will see ripples form. The ripples are very pronounced at first impact, so the place where the stone is hit, and then the ripples start to fade away with distance. And that's because the energy that's imparted is being dispersed over the mass of the liquid in which you drop the rock. Signal propagation in wireless signals operates very much the same way. We need to know whether or not a signal is dependent on line of sight or penetration. Line of sight is when a signal travels in a straight line from transmitter to receiver. If we encounter an obstacle, the signal may do a couple of things. It can either pass through it, depends on the type of obstacle it is, be absorbed into it, or be subject to any of the following phenomena over the next two slides. Fading, which is where as the signal runs into obstacles, its energy will degrade and eventually lead to a drop connection or just a slow transmission. It may also lead to attenuation. If you remember attenuation in a wired connection, it's where the signal weakens as it moves away from its original transmission point. From the source, we will lose signal until we reach a point where the signal no longer moves forward. Or if it does move forward, its degradation is such that it's no longer usable. So how do we correct this? Well, we either increase the power of the transmission at the origin, or we repeat the signal from a closer broadcast point called an extender. Extenders are not uncommon. It essentially does what we would do with a router, switch, or hub. It receives the frame, automatically regenerates it by means of interpreting its either 1 or 0 state, and then repeating it. You can also see that signal propagation is subject to interference. Wireless signals are much more vulnerable to noise because you can't shield a wireless signal. There's also no conduit that can be put at perpendicular angles to another. You end up dealing with what's called the signal-to-noise ratio of wireless signals in a much more direct sense than you would with a wired one. The signal-to-noise ratio, or SNR, is the proportion of noise to the strength of a signal. And when we talk about noise, it's just static, if you will. It's non-usable data. Refraction. This is where a wave travels through objects and alters the speed, direction, and or wavelength. So refraction you can think of when you stick your hand into a pool or a pond or some other body of water. You notice that your hand looks almost disconnected from your arm because the angle of incidence that the light passes through changes the angle at which your eyes are perceiving your hand versus perceiving your arm. Same thing happens with the digital or wireless signal. Deflection or reflection. This is where you have the signal bouncing back towards its source. Scattering is where you have diffusion in multiple directions, and diffraction is where the signal is kind of like refraction, except instead of just changing the direction, the signal actually splits into secondary waves. So if you see a prism, for instance, if you have a white light that goes into one end of a prism, the process of diffraction will actually cause it to split into the rainbow pattern that we're so used to seeing. Those individual subspectrum interfaces are being broken apart further and further so that your eyes are able to differentiate between different colors. Multipath signals deal with how to get a wireless signal to a different path in order to get it to its destination, getting around a particular barrier or passing through it. Our advantage using multipath signals is that there's a better chance of reaching our destination. Our disadvantage is that the delay of trying to move around objects can lead to data errors. If there's inconsistency in the order in which things are delivered, or if there's a checksum error, that can cause a lot of problems as well. So multipathing, while useful, can still have its pitfalls. Now let's talk about the IoT, the Internet of Things. This is made up of any device that can be connected to the internet. So a lot of people think of the IoT as being, really kind of fringe devices like a coffee maker that you can control with your phone, but it's anything that can be connected to the internet. Your computer is technically an IoT device. It just hasn't necessarily been configured to control a particular device, such as a lock or a light or a security camera. Personal monitoring devices are one of the fastest growing areas of IoT, so being able to tell if your water heater is leaking in your basement, or even something like your smartwatch that has a health monitor in it. All of these devices within a home create a type of LAN that we refer to as a HAN, or Home Area Network. A WPAN, or Wireless Personal Area Network, also includes short-range technologies such as Bluetooth and Zigbee. PANs, or wireless PANs in general, rarely exceed about 10 meters in any direction, so it's less than 33 feet in radius. The most common wireless technologies used to connect WPAN and HAN are discussed next. So Zigbee is one of the first substandards that we've dealt with. That's the first one that I ever discovered when I was doing my undergrad. 802.15.4. So it's a low-powered, battery-conserving wireless technology built to handle small amounts of data. It's great for what are called ISM sensors, industrial, scientific, and medical. And they're used in IoT devices for building automation, HVAC control, automatic meter reading, and fleet management. Tracking where things are, being able to send control signals, very handy thing for Zigbee. And again, the low power battery conservation means that a device can sit idle for a long period while still listening for data input. ZWave is a smart home protocol that provides two basic function types: signaling to manage a wireless connection, and control to transmit data and commands between devices. A ZWave network controller, traditionally called a ZWave hub, receives its commands from a smartphone or computer and relays them to various devices on the network. ZWave transmissions can run up to 100 meters per hop, so you can actually cover a fairly large amount of area. It can tolerate up to 4 hops through the repeaters, which puts you at over 1,300 feet of coverage. Bluetooth operates within the 2.4 to 2.4835 band. It hops between frequencies within that band to help reduce interference. This is something that was developed during the World War, the Second World War, as being able to move between different frequencies. The close proximity necessary to form a connection means that you have to be within a couple of feet to be able to connect to a Bluetooth device, and maintaining signal strength depends on what class of Bluetooth you're using. Before Bluetooth devices can connect, they have to be paired, and there are sometimes what are called multi-point pairings that can be done, so just be aware of what type of pairing your device supports. Again, as always, read your documentation. Bluetooth interfaces, because they are wireless and because it's a simple pairing operation in order to connect to it, they're susceptible to a number of different security risks. Blue jacking is where a connection is used to send unsolicited data, and blue snarfing is where a connection is used to download data without permission. So here we can see a couple of different classes of Bluetooth devices. Class 1 is industrial Bluetooth, and that's used at 100 milliwatts, and that is up to 100 meters in range. 2.5 milliwatts covers up to 10 meters. It's used for mobile devices, and 1 milliwatt covering up to 1 meter. It's very rarely used. And if you'll notice, even though we're going up by a factor of 10 each time, the power is not necessarily bearing that out. If we were going for 1 milliwatt per meter, we would expect the 2.5 milliwatt to be able to cover, of course, 2.5 meters. Instead, it covers up to 10. We don't necessarily see that scale entirely linearly because the 100 milliwatt to 100 meter is still lining up. See a little spike in the middle. ANT Plus, or ANT Plus. The ANT protocol was an ad hoc wireless protocol currently owned by Garmin and developed in 2004, operating at about 2.4 gigahertz. So it's around the same range as Bluetooth. Now, this is a fixed frequency protocol, and it gathers and tracks information from sensors embedded in things like heart rate monitors, GPSs, or other activity monitoring devices. So the Nike Plus enhancement for running shoes, there were several chest bands that you could clip on that would allow you to monitor heart rate and things like that. It can also sync data from multiple devices for the same activity. So let's say that you're on a bicycle, or if you're on a stationary bike, or if you're on a weightlifting machine of any kind, you're actually getting multiform information from the weight machine. Say you're on a Nautilus machine, it's able to tell how much weight you're pulling, as well as the biofeedback from whatever your smartwatch may be monitoring. RFID, radio frequency identification, is going to use electromagnetic fields to store data on a small chip known as an RFID tag. It'll include a transmit and receive antenna and possibly a battery. Some of the passive tag models are essentially agitated by the radiation from the reader, the electromagnetic radiation that is emitted, in order to pass the information that it is stored. If you have a pet that has a microchip, this is what it's actually using. It's using an RFID chip with a passive tag, so it's an ARP-T at the vets. A PRAT, or passive reader active tag, is a little bit different. This is where the tag has its own battery and can be tracked as it passes by several readers that are not automatically scanning. Active reader active tag is where you have a battery powered tag that has to be an engaged reader in order to use it. RFID is commonly used for inventory management. You may also see an RFID tag in your credit card if you have a credit or debit card with a contactless payment point that can be tapped onto a reader. NFC is a form of RFID that transfers over very short distances. The signal can be transmitted one way by a tag, and when employees need to access a secure area, it can be used as a form of ID. So if you've ever used the parking deck downtown on Nutt Street at main campus, that's an example of using a smart tag with your ID card. The NFC tag collects power by magnetic induction. So essentially you have a magnetic radiator device, an antenna that produces that signal, and it causes a vibration that can be converted into energy in the NFC tag itself. Wireless USB, this is based on the ultra-wideband radio platform. These products mimic wired USB 2.0, and I believe there is an ultra-wideband variant now that uses 3.0 as well for certain speeds. I think they're treating it more like 2.5. Now, it also has similar security and ease of use because it is over such a short distance. The radios here transmit between 3.1 and 10.6 gigahertz. Infrared, which is most people consider a legacy technology, is used primarily to collect data through various sensors. It exists just below the human visible spectrum. So when we talk about infrared, infra meaning inside, red is the slowest wavelength of light that human eyes can perceive. So if we talk about the upper end, we're talking about ultraviolet. So that's the ultra meaning above, and then violet being the fastest wavelength that we can perceive. So the presence or level of liquid can be something that IR sensors can use. There's a different level of diffraction and response that the IR sensor can pick up. Variations in the skin caused by variations in blood flow. So that's how your smartwatch is able to read your heart rate. It's able to tell proximity by essentially using interferometry to tell the difference between where an object is in relation to the sensor, because the variation in the wavelengths bounces back, and commands to a control device, which is more so what we're used to when we talk about the remote for a television or for any kind of input device, so like a projector. Speaking of, we can see here at the end of the remote near the front in the center, we can see a little glass bead. That is the IR transmitter, and when we press the button, it sends out a pulse. That's what's called a discrete code. That discrete code provides a particular command matched to a button, which then allows the projector to interpret that command and provide the appropriate output. WLANs work at OSI layers 1 and 2, and they support higher layer OSI protocols and operating systems. So wireless LANs, of course, are again going to be declared by the physical and data link layers, although various aspects of them are affected by upper layers. The most popular that we use for WLANs is Wi-Fi. That's the 802.11 committee. There are several substandards: A, B, G, N, AC, AT, AQ, Wi-Fi 6. Anything from 802.11n and on modifies how frames are used at the max sublayer to increase speed of signaling as well as range. The LLC sublayer is primarily concerned with multiplexing, flow and error control, and reliability, things that we deal with for the most part at layer 4 when we get into TCP. So here we see several different standards and their comparisons as far as frequency band, maximum theoretical output, and geographic range. Now, 802.11 MAC services, when we talk about access methods, append a 48-bit physical address to a frame to help identify the source and destination. It's the same physical addressing scheme as other Ethernet networks, allows very easy combination with other IEEE standards. Wireless devices are not designed to simultaneously transmit and receive. They operate in what's called half duplex. They cannot prevent collisions, and they use a different access method than Ethernet. One of the contention-based access methods we deal with is called ChasmaCop. Carrier sends multiple access with collision avoidance. The wired version of this is collision detection. It minimizes collision potential by using acknowledgement packets to verify every transmission. Now, this does require more overhead than standard 802.3 and less throughput, but we are able to connect wirelessly without having to maintain a physical connection between 2 points. The RTS-CTS protocol, request to send and clear to send, is a type of acknowledgement that ensures that packets are not inhibited by other transmissions. It's great for large transmission packets, but it does increase loss and potential overall loss of efficiency. So it's not always the best, but again, we're just trying to make the best analog we can with wireless transmission. So here we can see ChasmaCop with acknowledgement versus with RTS-CTS. In the top, we can see that it's basically just looking for activity detection. If there is or is not activity, there will be a brief pause, but if there's no activity, it will attempt to send the transmission afterwards. With the CTS-RTS, it's going to do the same brief pause, but it's trying to confirm a receipt from the host that it's intending to send to before sending the transmission. So it's like playing Marco Polo. The process of associating a host to an access point is the process of exchanging a packet between the two in order to confirm internet access. So this is part of the MAC sublayer. So we have what's called scanning, which is the initial process of trying to find a network. The survey will go through for an access point trying to find what's called a probe. So the probe is going to be transmitted as it's going through the different networks that are available. Passive scanning listens for a response known as a beacon frame. In that beacon frame, they'll most likely going to be what's called a service set identifier, the SSID. This is a unique string that identifies the access point It allows for better security and easier network management. Rather than having a random alphanumeric string, you can have something like FBI surveillance van 1, and you know you're connecting to the right network. You also will sometimes have what's called a BSS, or basic service set. This is a group of stations that are sharing an access point to create a network. The BSS ID, or basic service set identifier, identifies the group of stations rather than the access point. An ESS, or extended service set, is a group of access points connected to the same LAN. This allows roaming, where you can move from one BSS to another without losing connectivity, very similar to how a cellular network operates. As devices move between BSSs within a single ESS, connecting to a different AP requires a process called reassociation. Now, by simply moving from one zone of influence to another, there is a potential for a high error rate, especially if you have one access point within the ESS that has congestion. So here we see a single BSS network. Everything sends and receives from that one access point. Here we see multiple BSSs that will connect several devices together, and they're all within an appreciable range of one another. The types of overhead that are required to manage access to an 802.11 network would be, as we talked about before, probes and beacons, as well as the ACKs that we use when we're talking about CTS, RTS alternatives. 802.11 specifies the max sublayer frame type, and there are multiple frame type groups. Management frames can be used to associate and reassociate APs. Control frames deal with ACK and RTS for medium access and data delivery, and data frames, of course, carry the data that is sent between stations. Here we have a comparison between a data frame for 802.11, that's what we call a raw data frame, versus one that's been formatted for Ethernet. Because the 802.11 is wireless, we notice now that we have 4 addresses instead of just 2. That's because not only we have source and destination, but we also have to have the transmitter and receiver addresses. So the sequence control field, which is another field we have in 802.11 that we don't in 802.3, is the potential for fragmentation if we have to separate a large packet into smaller pieces. Error checking and fragmentation are also handled, but specifically at the max sublayer. Now with 802.11, we found a couple of innovations to make our lives a little bit easier. One of which is MIMO, the other is a variant of this called MU-MIMO. MIMO stands for multiple input, multiple output, and MU at the front of MU-MIMO is multi-user, so a lot of multiples involved. Multiple access point client device antennas can issue a signal to one or more receivers. The more antennas, the more that they're able to distribute the load, the better the range and throughput of the network. MU-MIMO allows multiple antennas to service multiple clients simultaneously to help reduce congestion. This is available with Wave 2 802.11 AC products. So anything with AC band or newer should be able to support MU-MIMO. There's also what we call channel bonding. Now most of our channels are 20 megahertz in width. We can bond 2 of them together to make one channel that's 40 megahertz in width, which can double the bandwidth available in a single channel. So if we don't have quite as many subscribers, we can make sure that the channels that we do have are maximized in terms of their available bandwidth. We can also use what's called frame aggregation. This combines multiple frames into one larger frame. We have 2 techniques for this. We can either do it using a service data unit or a protocol data unit. Now this does reduce overhead because you don't have to have the same amount of information for one consolidated frame as opposed to several micro frames or smaller frames. So here we see the difference between AM-SDU and AM-PDU. We see that the difference in frame size is pretty significant, almost 8,000 versus over 65,000 in the N band, and between 11,500 and 4.7 million bytes in the AC band. Pretty significant modification given frame aggregation. So here we see those frames as they can be modified. You can see that the payload is significantly larger as far as just a single frame with AM-PDU. Now let's talk about implementation. This section is going to talk about wireless LAN technologies, how to design small LANs, and how to configure access points and clients on larger networks. Wireless networks are not laid out using the same topologies as wired networks as you might imagine. You know, hub and spoke, point to point doesn't really work. We have what are called ad hoc and infrastructure networks as well as mesh. An ad hoc network is where there's no infrastructure device in between, such as an access point or a router. We just have direct transmission between them using their own Wi-Fi radios. Infrastructure networks are where we have an access point involved that accepts wireless signals from multiple nodes and then retransmits them to the rest of the network. A mesh network is where several access points work together as peer devices to help distribute the access load. So here we can see an ad hoc WAN, again, all devices communicating directly with each other with no infrastructure. Here we can see an infrastructure WLAN with an access point connected to a switch, and the switch passes to the backbone. Here we can see a mesh WLAN where we have two access points daisy chained together, again passing back into a backbone device. Centralized wireless management is made possible by a lightweight wireless protocol. Cisco has a proprietary one called Lightweight Access Point Protocol, called LWAP, and then they also use one called CAPWAP, Control and Provisioning of Wireless Access Points. That's a bit more common. CAPWAP is the one that I've used most in my career. A wireless controller can provide centralized authentication for clients using something like Radius or TACACS, load balancing, channel management, and detection of rogue access points. Rogue access points are no fun. You don't want to have an access point on your network that you don't actually control. Wireless technology can also be used to bridge two different parts of a LAN or two separate LANs. So here we can see a wireless connection being shared between access point A and B, each of which has their own subnetworks and their locations that they support. So whenever we're setting up a small home office type of network, we have to consider what's the purpose of the network, what are we going to support, how many devices do we need. This is often going to combine one access point that uses switching and routing as well as AP functions in one device. It'll connect wireless clients to the LAN and act as an internet gateway. There are also some devices that you might purchase that combine your cable modem with your router. I'm not really a fan of those. I feel like they're less easy to script in terms of troubleshooting, but they are functional. Whenever we're deciding where to install an AP, we need to consider a couple of things. What's the range that this thing covers? What's the distance from our location, our primary location? How many obstacles may be present, and what type of them? Interference, is there going to be a source of interference for noise from a large motor or from other wireless networks in the area? Are we in a building where there are going to be multiple APs conflicting with one another? Do we have channel modulation to be able to support non-overlap? Larger WLANs warrant a much more systematic approach to access point placement, and this usually involves planning what's called a heat map. We use a site survey to assess our requirements, facility characteristics, and coverage areas, as well as possible points of interference or lack of signal coverage. So we're going to determine our access point arrangement using reliable wireless connectivity within the given area after doing this planning phase. A thorough site survey may include things like studying the blueprints of a building. There may be certain buildings that are built with metal frameworks that are going to absorb or impede the ability of a wireless network to conduct its business. Are we going to use wireless access points as bridges in order to create remote wired access? Do certain floors need multiple APs? Do we need multiple frequencies being delivered? Do we need to test the strength from other WLANs to make sure that we're not getting overlap? Then of course we need to make sure we test that access. Make sure that we are aware of how the materials used in objects that aren't always present in the environment may interact with the design, and how wireless portions of the LAN will integrate with wired portions. Wireless-wired integration will often determine whether or not you need to place a second AP, or just make sure that the AP that you have is able to carry a little bit more traffic. After we do our survey and we identify and verify the quantity and location of access points, we're ready to install them. So we're going to go ahead and set up the ESS, set up the ESS ID, and make sure that the BSS for each individual station is in fact functional. Enterprise-wide WLAN design considerations often deal with, as we talked about, wireless and wired integration, and that's important to make sure that if we have wireless guest services, that they're not interfering with wireless business services, and vice versa for the wired networks. APs will often vary in the standards that they support, as well as their antenna strength and other features, the length of the power cable being able to reach a particular area, and there are a number of variables that have to be set during installation. The administrator password, of course, we should always change from the default, the SSID, whether or not said SSID is broadcast, various security and encryption options, and whether or not we're going to use DHCP or static assignment. Configuration is always going to vary from one client type to another. If the AP is broadcasting its SSID, clients in the vicinity will detect it and, of course, offer the option to associate it with it to each individual end device. Now, there are two processes directly related that we also hear about with this: onboarding and offboarding. This is where we're essentially adding or removing the ability of a device to connect to a network. So if we have a trusted access protocol that we need to use, we can sometimes download what's called a profile in order to allow that particular access. If we need to remove it, we want to be able to do it not only with the device in hand, but remotely in case the AP is lost or stolen. 802.11 standard security is non-existent by default. The only item that we need to connect to a network is the SSID. Now, if we want to compare for the processes of authentication, we have to have a database in which we can identify a particular client. That's providing a password or an individualized username. We can also use what's called MAC filtering. This is where we whitelist the MAC addresses for devices that we wish to use, and we'll ignore any other requests. We can use encryption to scramble data or make it at least a little bit harder for an outside observer to try and read. One of the protocols that we will sometimes use is what's called WPA. This is going to dynamically assign every transmission its own key. And there is a replacement that has come out called WPA2. It's a much stronger protocol. Most secure combinations of encryption would be combining a radius server with WPA or WPA2, and this communication type is known as WPA Enterprise or WPA2 Enterprise. Additional security options would be things like setting up a separate guest network. A lot of at-home SOHO routers now facilitate creation of a guest network just by clicking a slider. Setting up a captive portal. Essentially, the first page that a client sees in the browser when connecting is to require them to agree to a set of terms and conditions before gaining further access. If you go to Barnes & Noble, if you go to the library and you connect to their Wi-Fi, there will often be a capture page that you will have to acknowledge first before moving on to the next sequence. Security threats. This one's a little bit older, but it is still done on occasion. It's now more so done with cellular devices than with laptops. War driving is where a hacker is searching for unprotected networks by driving around with a packet sniffer that's connected to their laptop. And it's essentially just trying to find data transmissions that it can interpret and find the source of so that it can find vulnerable points to try and redirect their own traffic. War chalking is part of the war driving experience, where hackers will draw symbols with chalk on the sidewalk or on the wall near a vulnerable AP to make it known to other hackers. An evil twin is a rogue AP planted in the same geographic area to pose as an authorized AP to try and funnel that traffic to them instead of the legitimate source. WPA attack. This involves interception of network keys communicated between stations and APs, also known as WPA cracking. So if you remember, WPA deals with giving every communication on a network its own individual key. If we can break that key, then we can view the conversation. WPS attacks are where we use a pin to try and access an AP's settings. So for those of you who have a push-button WPS function on your router or switch, that is the type of attack you would be vulnerable to there. It can be cracked through brute force, usually because the default pin is not changed when we set that up. I often disable WPS on my devices for that particular reason. Now, if we're trying to troubleshoot a Wi-Fi network, we can't use the same tools we would for a wired network. Continuity and performance testers aren't going to tell us anything about wireless connections, won't tell us anything about the stations involved or the APs. We have to use tools that specifically will deal with a wireless NIC and testing wireless protocols, so things like a spectrum analyzer. The spectrum analyzer is going to assess the quality of the wireless signal as it is just as radio frequency waves. If we need something that's a little bit more in depth, we'll have to get a Wi-Fi analyzer, which can evaluate network availability, optimize Wi-Fi signal settings, and help identify potential threats. Now, some capabilities common to these testing tools would be identifying transmitting APs, stations, and channels, as well as measuring signal strength. If we know those four things, we can usually know quite a bit about the potential vulnerability of an AP. We can also indicate the effects of attenuation, signal loss, and noise, so we can see where potential obstacles may be. We can interpret our signal strength information, as well as ensuring proper association and reassociation between APs. Eliminates a lot of evil twin spoofing. Capturing and interpreting traffic, as well as measuring throughput and assessing transmission errors, and analyzing characteristics of each channel. Maybe because of a particular device in the area, there is a particular channel on the device that is being interfered with. And as such, we want to maybe skip over that channel as we're doing adaptive frequency hopping. Wireless configuration pitfalls to avoid. Of course, we want to avoid setting the wrong SSD, setting the wrong type of security. You don't want to put in a WPA2 password on a WPA device simply because it won't read correctly. The passphrase may be wrong. Overlapping channels, mismatched frequencies, mismatched standards. An A-band device, which it would be laughably old at this point, would not do much good if you're trying to connect to it with a G-band device, or vice versa. Incorrect antenna placement, interference, simultaneous wired and wireless connections. That's usually where somebody's done a poor job of setting static IPs. Problems with firmware updates or compromised firmware. If somebody's accidentally downloaded a virus or malware version of a particular firmware, that's usually no good. Unoptimized access point power levels, that can cause voltage spikes. Inappropriate antenna types, and then of course client saturation. That's probably one of the easiest ones to hear about. You just got too many people connected to one access point. An omnidirectional antenna placed high near a ceiling broadcasts a signal to all directions, but is mostly inaccessible to workers on the floor. So let's say that we've got an antenna that's placed up above something in order to provide Wi-Fi access for the security cameras, but not necessarily to the workers on the floor of like a warehouse or something similar. That would be an okay implementation for an omnidirectional antenna. A unidirectional antenna would probably be a little bit better because it can be positioned near the ceiling but aimed at the floor, meaning that the focus of the signal is to the workers, not necessarily to just perimeter devices that could be wired. So that is our chapter. Let's go ahead and take a peek at the summary here. Obviously, I won't make you read that. If you have any questions or concerns, you can always email me, as you normally do, at jearmke063@cfcc.edu, or you can contact me at my Google Voice number, 239-7814. Hopefully you have a wonderful rest of your week, and if you have any concerns, as always, please let me know, because if you have a problem, it's entirely likely that someone else does as well. I hope you guys stay safe and well throughout the remainder of your week, and I will catch you next class.